All right, here we are continuing on with exponential growth, lesson 1 in unit 7. We're going to look at example number 2. So example number 2 gives me an exponential equation. Y equals 2 times 6 raised to the x. And when we're talking about these exponentials, you'll always be able to tell it's an exponential because the variable will be the exponent, hence exponential function. That's how you know. And that 6, remember that 6, if we're talking old school like exponents, like base raised to an exponent, a b raised to an e, that 6 is the base that's being raised to some exponent. That 6, remember, what do exponents represent? Well, coming back up here, those exponents, let's jot that down. Remember, let's actually put it up here. I'm so disorganized today with this. Remind yourself that exponents, back from 7th grade, represent repeated multiplication. And that makes sense because if you go back and look at our first example here, you can see that we are repeatedly multiplying that 2. We're keep doubling, multiplying it by 2, making this an exponential relationship. So that means if I were to try and write the equation for this equation would look something like number of people. So people is equal to that number that I'm repeatedly multiplying. That base is going to be that 2. It's always going to be raised to a variable. The other variable I'm using here is hours, or h. And then that starting point. What was that starting point? My starting value right here, I'm just going to circle this and label this. This was that starting value, or fancy words make us sound smart, INIT, initial value of 3. And that goes in there. So right there, the equation for this exponential relationship is y equals 3 times 2 raised to the x. Or, using the variables they asked, p equals 3 times 2 raised to the h. So one last thing I'm going to throw in here is that you'll notice that the bases in all these examples, that 6, that 2, the base, in order to represent exponential growth, the base, let's just add it in right here. The base, aka the number being raised to the exponent, will be greater than 1. And that makes sense because in order to show growth, in order for a number to be bigger than what it started as, you need to multiply it by something bigger than 1. Could it be equal to 1? If I multiply something by 1, is that going to make it grow? The answer to that would be no, because if you're multiplying something by 1, it's going to stay whatever it is. 7 times 1 is 7. 8 times 1 is 8. It's not going to grow if you're multiplying it by 1. So it can't be equal to, but it can be bigger than, or has to be bigger than. Okay, let's actually do this last example here and call it a day. So we're going to make a graph and then find the average rate of change. So before I can make a graph, I definitely need to plot it in here, and how convenient for us that I already have it in there, 2 times x caret to the 6. I'm going to go to my table. Ooh, lots of big numbers. So we're definitely going to need to do some editing and like scaling on our graph here. Otherwise, we're not going to be able to fit any points. So I'm just going to go up by 10s because that seems to be a solid plan. So 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Okay. Just telling me to sketch a graph, so it doesn't have to be perfect. So just noticing that in terms of, let's take a look at it. Oh, you can tell right here, I'm super zoomed in because this is a 1 mark and this is a 1 mark. So I'm going to go back and zoom standard that thing. Boom. So you can see that it's not linear. It's not a straight line. It's exponentially getting larger. You know, it starts off and then boom, shoots up. But again, not perfectly straight up and down. Otherwise, it wouldn't be a function. So it's not a vertical line. That's why I kind of zoomed in on that thing. And also, I want to point out, it might look like it's going to touch and kind of blend into this x-axis here. But when we do zoom in, enter, you can see, well, not really. Let's try that again. Let's zoom back out and go this way. Calculators are very particular. You can fast forward through this if it's a little too... Okay, and so now I'm going to try zooming again, but this time I'm going to target my zoom. So instead of trying to zoom in over there, I'm going to move that guy and zoom in over here. And that did nothing for me. Awesome. Cool. So, well then, your calculator isn't perfect, as I'm sure you know. The main important thing that's happening here is that if you're looking at these decimals, remember old school scientific notation from like 8th grade? These are the tiniest decimals, getting really, 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 really close to 0, but never actually touching 0. These points never actually get to 0 here. They get really close to it, but never actually touch it. So when you're drawing that, it's really important. That's a terrible graph. Let's try that again. It's really important that you don't make your graph cross that x-axis. That's going to have to be good enough. You will lose credit if that crosses below that x-axis because like we talked about, it gets really, really close to 0. Gets really close to 0, but it never actually crosses that x-axis. It never actually becomes equal to 0. Really important to make sure you know that. Okay, so there's our graph. And next, average rate of change. Really important that you know what average rate of change is. Hopefully, change in y over change in x is jumping into your head. Between, they're giving me an interval. This is the interval for me to do average rate of change, not for graphing, because they told me to sketch a graph. So 0 and 5, based on that letter in the middle, those are x values. So 0, comma, 5, comma, oh no. My computer's losing battery. It needs to be plugged in. There we go. And again, you can either plug that in by hand or just use your table here. So 0 is 2, and 5 is, 15,552. 15,552. Okay, so using that, I'm going to do my change in y over my change in x. I always label my points because I mix that up like it's my job. 15,552 minus 2 over 5 minus 0 is equal to 15,550 divided by 5, which, second quit, 15,550 divided by 5 is going to be 3,110, because 5 goes into 15, 3, once, 0. So, making sense that it's a positive because that graph is increasing or going up. So that is my average rate of change. If I were to do a different interval, like 2 to 3, that would be different than 300 or 3010 because of the fact that it's not a constant rate of change, making it not linear because it's exponential.